So we're going to talk specifically about a couple of specific types of transformations today, dilations, and then we're also going to use vectors, and vectors kind of replace what we did yesterday. So today kind of goes off of yesterday a bit, or quite a bit. So what am I doing? Okay, so dilations, reminder, is when we either enlarge or shrink something. So make something bigger or smaller. And if you guys notice, similar to how we added or subtracted a number to the x and y here, now we're multiplying by something. So k is basically our scale factor. And that's how much we're enlarging or shrinking it. And depending on what k is, it's going to either enlarge or shrink. So if k is greater than 1, then it's going to enlarge. So that's k is greater than 1. Now if k is in between 0 and 1, it's going to reduce or get smaller. Oh, it's not negative. We don't really deal with negatives much here. Because if it's negative, it actually will like flip it as well. And when we do this, rather than our shape looking exactly the same, they're going to be similar shapes, but not the same size. So they're going to be similar, not congruent. So we have our coordinate points here. And this one is a little bit tougher to do where like yesterday we were able to say, oh, I'm moving it right 5 and down 3. This one we're gonna have to do a little bit more work with our coordinate points. So I'm gonna start by graphing this first shape here on our graph paper. I think almost everything today like should be like steps of 1. I don't want to say that for sure. There might be a few that they went up by 2s or something. But -8, 4. So this is a pretty big 4-sided shape here. So it takes up a majority of the graph. So you probably are hoping that this is going to end up being one where we're going to reduce the size, because if it has to go bigger, then we're going to be well off our graph. So, and that makes sense that it says dilate with a scale factor of 1/4. So basically we're saying shrink this down to 1/4 of the original size. So what that means we do is we take all the x and y values and multiply them all by 1/4. So I basically am going to write my new coordinate points. And remember yesterday we talked about it, just rather than calling it something other than E, we're going to call it, they call it E prime. So it's E with like a little apostrophe, or almost looks like a first power. and I'm multiplying that by 1/4. So I'm basically taking 1/4 of all of these. So 1/4 of -8 would be a -2, basically dividing it by 4. 1/4 of 4 would be 1. Bless you. Now, hopefully, you'll get numbers that work out nicely. I won't guarantee that will always be the case. Typically, when I make the questions, I try to make them so they're all reasonable numbers to take like 1/4 of. At the very least, hopefully, like a decimal that seems easy enough to put on the graph. So now we'll graph that, and we're going to see that this was shrunk down to 1/4 of the original size. But it should still look like the same shape. So the mini shape inside of the bigger one. So that would be dilations, so smaller, larger, depending on the problem. So the next one, very similar. Now this one, rather than using 1/4, they're using a decimal. So they're saying dilate the scale factor of 2.5. So again, I'm going to put this first one on here. Now again, being careful about like something like 0.3, that's one that a lot of times we get messed up. If you put it in the wrong spot, your shape might look funny and then it might make it harder to make it fit on the graph or whatever it happens to be. So just be careful about that. And just using a little bit of logic here, I'm hoping this next one obviously is an enlargement because this is pretty small. So if I had to draw a smaller shape than this, that would be really annoying. So it says dilate the scale factor of 2.5. Since 2.5 is bigger than 1, this is going to be an enlargement. Now this one you might have to grab a calculator for depending on your comfort level with multiplying by something like 2.5. None of the numbers are too crazy. But I'm basically taking all of these numbers and multiply by 2.5. Like 2.5 times 2 is just 5. And so just being comfortable with having to graph something like a 2.5 is an estimate where you're going to put it. It's not going to be perfect. But again, I'm assuming this is going to be an enlargement. And so showing this one does a little bit of overlapping. And that doesn't mean we did anything wrong. It's just the way the space turns out. It's just the way that it happened, that it ends up overlapping, and that's perfectly fine. But it's an enlarged version. It's 2.5 times the size. All right, questions there? When you're ready, let's flip the page. So the next question is asking us if something is an enlargement or reduction. They give you the drawing already, and then they ask you to find the scale factor. This actually takes us back a few chapters when we were doing scale factor. So not a bad thing for us to review. So A to B. Now, this should be something you should be able to eyeball. If I'm going from A to B, is it getting bigger or is it getting smaller? A is smaller than B, so that means it's an enlargement. So this is bigger. Now they ask us the scale factor from A to B. So we're going to compare some of these sides, and then I'm actually going to tell us, let's find some of the other missing sides. They're easier than you maybe think. So like for instance, like the shorter side 2 would go with 5. So I would say this is a 2 to 5 scale factor. And at the same time, if I know this is 5 here, and this is 5 here, y should also be 2. And then also, if I wanted to find x, I should be able to find that because it's just a missing side using the same scale factor. So 2 over 5 would go with, and again, it's been a while since we've done this, x would go with 7.5, but x is the smaller one, so I'll put that one on top, and then we'll cross multiply. So I would figure out that x is 3, but then z would also be 3, because that's a little rectangle there that, based off of the information they gave us, we can make those assumptions. So again, this was something like, so if you guys recall, I mentioned that, or if you look at the title of the section, it says 6, 7, there you go, and 9.1. So mostly this is a chapter 9 section, but 6.7 had this in there. I moved it out of there because I thought it fit better with this stuff, but at the same time, this dilations are really just working with scale factor, and we did that in chapter 6. So that's why this comes out of that section, but I think it works nicely with these other types of movements. All right, our last one here is kind of just another way to write what we did yesterday. So this is called vector notation. This replaces what we did yesterday. And you might say that was fine. Why are we replacing it? It's just another way to write it. So if someone knows something about translations, they would be familiar with this notation. It's called vector notation. A vector is basically like kind of like a ray. And what the vector is rather than using parentheses, we use these little like brackets. And that little plus or minus, that just means it could either be positive or negative. And so what they basically take out of this, they take the x out of it. So if you look down below, I'll use that vector notation 5, -1. It's just telling me that's how you're changing the x. This is how you're changing the y. So this problem here is an example of what we call a vector. A would be considered my starting point. And it looks like a ray. So a vector usually looks like a ray here. The terminal point would be B. And so what I would do is I'd talk about how much we move in the x direction. So to go from A to B, I would move kind of like slope, but in this case, we want the x first. So I'm going to move to the right. I believe it's 8 spaces. I'm counting blocks. So I move so the horizontal component for this would be +8. I move to the right 8. And then my vertical component in this case is going down. So this one would be a -3 in the vertical component. So the way we would write this vector is we'd say it's a +8 and then a -3. So that's considered our vector notation. So it's another way to do what we did yesterday. So this last question, we're going to basically use vector notation to translate our triangle. So they tell us our vertices here, I'm going to plot those. So I have this skinny triangle here. And they're telling me to translate it with 5, -1. So again, this is really the same thing as if I said x + 5, y - 1 from yesterday. But all I'm doing is it's telling me to move these right 5 and down -1. So I'm going to take all these points and move right 5 down -1. And so then our new triangle. Okay. So hope that seems reasonable. I get you guys your homework that goes with this. I kind of cut and pasted some 2 worksheets together. So just so you know, the numbering goes a little bit out of order. Oh, and just to remind you guys, make sure it's clear, is the original is called the pre-image. So, and then the new one is called the image. So there's a question they ask about that, and so just to be clear on that. Yeah.